Srimati R. Padmavati, Head of Department EC, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics, Oscillators and Amplifiers. Today we are going to see oscillators, in which Introduction to Oscillator, Borkhausen criteria, phase shift oscillator and Weinbridge oscillator. So this is the basic diagram to explain the concept of oscillation. So this is an amplifier A and this is the feedback network beta, and there is a switch. Initially, if the switch is opened and if we give an external input signal, actually for an oscillator we are not supposed to give an external signal, it has to generate the output without any input. But here initially, to give some output, to generate an output, consider that initially we are giving an input signal, and if the switch is opened at that time, so we are giving the input signal here, and this is amplified based on the gain of the amplifier. So after the amplifier, the output voltage is AVI, V naught is equal to AVI, where A is the gain of the amplifier, and the same voltage, the output of the amplifier, is given as the input of the feedback network, and whose output is beta into AVI, where beta is the gain of the feedback network, and the same voltage is again given as the input of the amplifier. Here feedback voltage is given as beta AVI. What is beta and what is A? Beta is the gain of the feedback amplifier and A is the gain of the amplifier. So if this beta A is chosen such that the feedback voltage is equal to the input voltage, that is what we have given externally. If this Vf is equal to Vi, then the output is the same as the input, right? This output, the output of the feedback network is same as that of the input network, right? So that is what the concept of oscillation is. If the switch is closed, then after that the switch is closed, this output voltage is given as the input of the amplifier, and it goes as the same procedure as number of cycles. So it produces an output. What we have told is, if the switch is opened and we are giving an external signal, input signal for an amplifier, so it gets amplified, and this signal is acting as an input to the feedback network, and it again gets amplified. It is multiplied with the gain of the feedback network, and if this beta A is chosen such that the output voltage is equal to the input voltage, then this output is going to be the input of the amplifier. Now if you have to close the switch and remove this voltage, external voltage, it goes on for the repeated number of cycles and it produces an oscillation. This is for the concept of oscillation, but practically we will not give any input signal. From the noise of an amplifier, it is producing the output voltage, and because of the amplifier it gets amplified cycle per cycle, and so the output will be a sustained oscillation. That is what in the practical case we will not give any input signal externally. This is the output of the oscillator. Initially there is a noise, surely there is a noise present in the amplifier output. So based from this noise only we are getting the sustained oscillation in the oscillator circuit. So here these are all the non-sinusoidal waveform, because beta A is not exactly 1, and this oscillation goes on increasing, and after one point it gets sustained. It is a sustained oscillation because the amplifier at one point it will get saturated, so you will be getting a saturated output, non-sinusoidal waveform due to saturation here. This is the steady state envelope limited by the circuit saturation. So this is the envelope, it is limited by the circuit saturation. So, the amplifier, if it gets saturated, you will get a sustained oscillation after this point. So, for an oscillator, there are two conditions to be satisfied if it has to generate an oscillation. One is the magnitude of A beta must be equal to 1, and next is phase shift of the loop gain A beta must be equal to 0 or 360 degree or integral multiple of 2 pi. See, these are the two conditions and they are called as Barkhausen criteria. These criteria must be satisfied by any of the oscillator. Different types of oscillators according to the range of signal generation or according to the type of passive components used. We are going to see the oscillator types RC phase shift oscillator and Wien bridge oscillator today. So, this is the circuit diagram with the help of the FET or with the help of the BGT here, both are given. So, this is the concept of RC network. RC phase shift oscillator is the oscillator type, and in the feedback network we have used 3 combination of R and C. Okay. So, in each RC network in practice it is going to produce 60 degree phase shift in each RC network. So, for 3 RC networks totally 180 degree phase shift will be the output, and the remaining 180 degree will be produced in the amplifier circuit. So, here also the same, the 180 degree by the amplifier, another 180 degree by the feedback network. So, one of the Barkhausen criteria is 360 degree phase shift or 0 degree phase shift. This was obtained by this RC phase shift network at the feedback. So, we have to derive the frequency of oscillation for this oscillator. So, at what frequency the oscillator is going to produce a sustained oscillation, that is what you have to derive. So, this is the formula. This is actually after you derive, this is the answer. F is equal to, that is the frequency of oscillation is 1 by 2 pi root 6 RC for FET, and for BJT this is the case. So, we will derive the frequency of oscillation from the feedback network. We have considered only the RC phase shift network. So, this is the output voltage. From here the output voltage is taken and this is the network. After the network, here is the output of the network, and that is said to be feedback voltage Vf, and all the capacitances are considered as equal, all the resistance are also considered as equal, and assume that the current flowing through the first network is I1, second is I2, third is I3, and now we are going to transfer this in a matrix form. So, you have to give an equation for all the loops. So, for the first loop it is I1 is flowing through the resistor R and the C capacitor. So, it is given as R plus 1 by Cs minus this resistance is common in the first loop and the second loop. So, you have to subtract the current from the second loop through this resistance R. So, it is minus I2R, that is equal to the output voltage. This is for the first loop, and for the second loop there are 2 resistors. So, I2 is the current flowing through these 2 resistors and also to the capacitor. So, I2 into 2R plus 1 by Cs, and this resistance is common to the third loop also. So, the current I3 through this resistance is subtracted, and also this resistance is common to the first loop. So, I1 through this resistance is also subtracted and it is equal to 0. This is for the second loop, and for the third loop there are 2 resistors through which I3 is flowing. So, I3 into 2R plus 1 by Cs, and this is the common resistor through which I2 is flowing. So, this has to be subtracted from I3. So, minus I2 into R is equal to 0. So, from this form the matrix. This is the coefficient of I1, the first column, second column the coefficients of I2, and the third one is the coefficients of I3. Here I1, I2, I3, and this is the voltage value for those equations. And if you calculate the determinant value of this particular matrix, you will be getting this answer. D is equal to R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1 divided by C cube S cube. So here if you calculate I3, the current flowing through the third loop, you have to calculate D3 by D. How will you calculate D3? For the third column you have to substitute the voltage value only for the third column. If you see this determinant, so for this third column you have to substitute this value for D3. I have substituted here and the answer is V0 R2, and I3, if you calculate it, D3 divided by D, it is calculated like this, and for S is equal to j omega, and if you considered alpha as 1 by omega RC, if these two values are substituted in this I3, you will be getting beta is equal to 1 by 1 minus j 6 alpha minus 5 alpha square plus j alpha cube. What is beta? This is the feedback factor of the network. Network we have considered as the feedback network. So, beta is this value. So, from this alpha 6 minus alpha square is equal to 0, because beta has to be real. The beta value must be real. So, the real, we have considered the imaginary part of this equation to be 0, and from this alpha is calculated as root 6. And what is alpha? We have used 1 by omega RC for alpha. Replace this term, and from this you will know what is f naught. Omega, we know that omega is equal to 2 pi f, and if you substitute omega here, you will be getting f naught is equal to 1 by 2 pi RC root 6. So, this is the frequency of oscillation for the RC phase shift oscillator, and here we know that beta has to be real. So, we have taken only the imaginary part, and that was equated to 0, and to know the gain of the amplifier, the real term is equated, only we have taken the real term, and real term is 1 by 1 minus, if you substitute this alpha in only in the real term of beta, you will be getting 1 by 1 minus 30, right, and it is equivalent to 1 by minus 29. And what is the value of A? We know that modulus of A beta is equal to, must be equal to 1. Modulus of A beta must be equal to 1 is one of the criteria of Barkhausen. So, to calculate the gain of the amplifier, from this beta it is known as A is equal to, calculated as A must be greater than or equal to 29. The mod value of A must be greater than or equal to 29. If this circuit is implemented with the operational amplifier, this is the gain formula, but we are using the FET amplifier, or if you use a BJT amplifier, these are the resistors which decides the gain of the particular amplifier circuit. So, according to that you have to design the gain of the amplifier, but for the frequency part of the circuit, this is the common frequency of oscillation. At this point only we will be getting the sustained oscillation, and also the Barkhausen criteria is also satisfied by this oscillator. So, here finally the frequency of oscillation is derived as f is equal to 1 by 2 pi RC root 6, and beta is derived as 1 by 29, and therefore, the gain of the amplifier must be greater than or equal to 29 to satisfy the Barkhausen criteria. The amplifier gain magnitude is calculated from mod A is equal to GM_RL, and RL is given as the parallel combination of RD, and this is the internal resistance small rd. So, parallel combination in the sense RD, the capital RD, which this capital RD is the resistance connected to the drain terminal of the FET, and this small rd is the internal resistance in the drain terminal of the FET. So, the parallel combination of these two resistors will give you the load resistance RL. From this you can calculate the gain of the circuit using the FET. We will have a break. Welcome back after the break. So, we have seen RC phase shift oscillator, in which we have derived the frequency of oscillation and the feedback factor of the feedback network, and how the gain of the amplifier is derived from the formula. And now we are going to see about the Wien bridge oscillator. In Wien bridge oscillator, why the name is called as Wien bridge oscillator is, we are using the structure of a Wien bridge for the feedback network used in this oscillator type. So, here what is the structure of the Wien bridge is, for a bridge circuit we know that it has 4 ohms. In 2 ohms of Wien bridge it has the resistors only, and in 1 ohm it has the parallel combination of the resistor and the capacitor, and in another ohm, that is in 4th ohm, it has the series combination of a resistor and a capacitor. So, here this is the bridge circuit, it implements with the same. These 2 ohms A, D and C, D has only pure resistances R3 and R4, and A, B is the ohm which consists of the series combination of the resistor R1, C1, and this B and C, this ohm consists of the parallel combination of C2 and R2. So, this is like a Wien bridge structure, and this structure we have taken it for the feedback network of this particular type of the oscillator, and so it is called as Wien bridge oscillator. And this feedback network is not going to produce any phase shift, and the amplifier also, because of this network does not produce any phase shift, the amplifier is also not going to produce a phase shift, because we know that the Borkhausen criteria is the phase shift must be equal to 0 or 360 degree. But in the case of the RC phase shift oscillator, the amplifier must produce 180 degree and the feedback network is producing 180 degree to satisfy 360 degree of the total phase shift. Here this in this circuit, this is the amplifier part and this is the feedback network part. So, from the feedback network we are going to derive the frequency of oscillation, and this is the Wien bridge oscillator using an op amp with the same concept. This is the amplifier part, this is going to produce the amplification, and feedback is given through these network, and this network is in the structure of Wien bridge, the same two pure resistors in 2 ohms and series combination of R and C, parallel combination of R and C in another 2 ohms. This is the feedback network. And how will you derive the frequency of oscillation? So, we are considering only the feedback network as in the case of the RC phase shift oscillator. Here in the feedback also only 2 ohms is considered, right. So, here to this node the output is connected in the circuit. So, across this node to the ground, across this point to ground, we have to calculate the output voltage. Across these 2 points we are going to calculate the feedback voltage. So, here this point is given as the input of the amplifier and this point is given as taken as the feedback of the amplifier or an oscillator. So, consider this is the output voltage and this is the feedback voltage. So, here beta is calculated as beta. What is beta? It is the gain of the feedback network and it is given as Z2 by Z1 plus Z2. What is Z2, Z1? Z2 is the parallel combination of the resistor and the capacitor, and Z1 is the series combination of the resistor and the capacitor. So, we have calculated according to the connection what is Z1 and Z2. It is calculated, and if you put it in the beta, you will be getting this term. You will be getting R2C1S by 1 plus R1 R2C1 C2S square plus S of R1C1 plus R2C2 plus R2C1. If you replace S is equal to j omega, beta will be like this. If you replace this S is equal to j omega, we know that S square will have minus omega square, S is equal to j omega. So, instead of this S square, you will be having minus omega square because j square is equal to minus 1. So, it is minus omega square plus j omega, the total term will come here. We know that the beta value must be real. So, the real term is equated to 0 here. Real term from this beta equation is 1 minus omega squared r1 r2 c1 c2, that is equal to 0, and from this we can easily calculate what is the frequency of oscillation. We know that omega is equal to 2 pi f. So, it has given us, if you substitute this 2 pi f here, you will be getting f naught is equal to 1 by 2 pi root of r1 r2 c1 c2, right. So, here if these values are equal, r1 r2 is equal and c1 c2 is also equal, the frequency of oscillation will become 1 by 2 pi rc. There is no root here, if provided the R values and C values are equal, and that is the frequency of oscillation. At this frequency, the oscillator will produce the sustained oscillation, and also it satisfies the condition of Barkhausen criteria. And what is the gain of the amplifier now? The imaginary part of beta is taken, and beta is, after cancelling out and after considering that the resistors are, all the resistors are equal and all the capacitances are equal in this equation, you will be getting beta is equal to 1 by 3. And if beta is 1 by 3, the value of A must be greater than or equal to 3, and this is for the operational amplifier formula. It is A is equal to 1 plus Rf by R1 is equal to 3. So, Rf is equal to 2 R1. This is the value of Wien bridge oscillator using operational amplifier, this particular gain term. But this beta and frequency oscillation is always common whatever the amplifier is used, whether it may be a BJT or it is a FET or it is a operational amplifier. Whatever the amplifier is used, the type of amplifier is used, the frequency of oscillation is common, and beta value, that is the gain of the feedback network, is also common, and so the amplifier gain is common. But based on the formula, the resistors used in the amplifier, the value will be, the formula will be changed, but not the value. So, finally, the frequency of oscillation is derived as 1 by 2 pi root of R1 C1 R2 C2 if these resistances and capacitances are equal. As I said, it is 1 by 2 pi RC, and gain of the amplifier as per the circuit, it is R3 by R4 is equal to 2 as per this circuit. For operational amplifier circuit, it is R3 by R4 is equal to 2. We will summarize what we have seen in the session. We have seen the introduction about the oscillator, how the waveform is generated or a sinusoidal waveform is generated. Initially, the switch is opened and we externally some input signal is given to the amplifier, which gets amplified and given as the input to the feedback amplifier, and again after the feedback network value is taken and it is given as the input to the amplifier. This is what the concept. So, if these two values, the output of the feedback network and the input is equal, then the oscillation will be generated as per the cycles going on, and after that the external input signal will be removed and the circuit is closed, and as number of cycles going on, the oscillations will be generated and it will get saturated, sustained oscillation will be obtained. But the oscillator must satisfy those two criteria, Barkhausen criteria. And what is the Barkhausen criteria? It is modulus of A beta is equal to 1 and the phase shift between the input and output is 0 or 360 degree. And we have seen the types of oscillators. We are going to see all the types of oscillators, and the classification of oscillator is based on the types of passive components used. You can use L and C, you can use R and C. You can use a bridge circuit, Wien bridge circuit in the feedback network. So, according to the types of passive components used in the oscillator and according to the range of frequencies generated by the oscillator is named as Wien bridge oscillator, RC phase shift oscillator, Colpitt's oscillator, Hartley oscillator, and so on. So, in the next session, in the remaining session, we are going to see the remaining types of oscillators. We have seen now the phase shift oscillator and the Wien bridge oscillator. In phase shift oscillator, why it is called as phase shift oscillator is, in the feedback circuit, we have used 3 RC pairs connected in series, These three RC pairs totally produces 180 degree phase shift practically, not in ideal case. In ideal case it produces 270 degree because each RC network will give you 90 degree phase shift between input and output, but in practice it is reduced as 60 degrees. So it produces totally 180 degree phase shift. To reach the Barkhausen criteria, we have to produce another 180 degree phase shift in the amplifier circuit, and so it is implemented with the help of the BJT or FET or operational amplifier, and so this oscillator is called as phase shift oscillator. And next is Wien bridge oscillator. Here the name comes because we have used the Wien bridge structure in the feedback network of this particular oscillator. So it is called as the Wien bridge oscillator, and in which we have derived the frequency of oscillation, and we have derived the amplification factor of feedback network, and so the amplification factor of the amplifier also. Try to answer for these questions. What is an oscillator? What are the conditions to be satisfied by an oscillator? Define Barkhausen criteria, and design a phase shift oscillator for the frequency 1 kilohertz. We know that the frequency is derived as 1 by 2 pi RC into root 6. So based on that formula, you have to assume the value of the capacitance as less than 1 microfarad, and calculate what is R, because frequency is given, and derive the frequency of oscillation for the Wien bridge oscillator. These are the references. Thank you.